Volume integration is similar as we are using in scalar function. Suppose for a sphere, we know the density at all points FD is density. This is a scalar function, just remember. And the volume of a sphere is V. So we find mass as density into volume. So here you can say that mass is volume integration of density function in this sphere having volume V. I will again repeat. This is a volume sphere of volume V, and density of this sphere at all point is same, that is Fd. Hence the mass of this sphere is simple density function and into volume, that is mass. So mass is volume integration, we will say, because here density and volume both are fixed, hence we can directly find volume integration or mass. But when this density is changing every day, suppose it is changing, then we cannot directly find density by multiplying with volume, because density is changing every day. In that case, we have to use integration method. So that is analogous to line integration and surface integration. In line integration, we have taken work done as an example, physical quantity, which is applicable for line integration. In surface integration, we have taken physical quantity flow, which is very familiar physical quantity, which uses concept of flux. But in volume integration, you can say mass is also a volume integration of a scalar function. Unlike single line and surface integration, line integration you have vector field dot dl, surface integration you have vector field dot dl. So these two vector operations are carried out with vector field along displacement vector and area vector. Unlike this, volume integration is carried out for scalar function f dot dv. In volume integration, f is scalar, unlike vector function in area and length, line integration and surface integration. F is scalar function, and dv is not a vector, volume vector like dA and dl. It is also a scalar volume. So volume integration is simply a scalar product of scalar quantities which are changing in a sphere. Then we use volume integration. Unlike these two, volume integration is carried out for scalar function. In vector calculus, volume integration is required to find divergence in a volume. We have explained the divergence. So divergence of a field is a scalar quantity. We have shown because it is del dot f. It is a scalar quantity. So this divergence is a scalar quantity. Divergence we have found at a point. So it may be same at all points. It may be constant at all points, divergence of a function of a vector field, or it may change at different points. Divergence may change at different points, but it is scalar everywhere. Hence, similar to this concept, mass, finding mass, density is changing at every point in volume, then we have to find mass by integration. Similarly, divergence is changing at every point, then we have to find volume integration of divergence of f dv by integration method. So in standard form, in vector calculus, we don't use mass, or I just use this concept, this terminology to explain it. But in vector calculus, we don't use mass as a quantity. We use volume integration to find divergence of a field. So we have just correlated this with this because both are actually same, but this is not used in vector calculus. Vector calculus you will use divergence as a scalar function. Here scalar function was density, but here scalar function is divergence. Into volume, into volume. Volume is not a vector function, unlike dl and dA in line integration and surface integration. So here it is written in standard term like this, but you should not think that this volume integration of divergence can be found only by triple integration, because it is simply divergence into volume. It can be found with simple formula. If divergence is constant, you can find simply by divergence into volume of a sphere, just like this, density into volume of a sphere. If density is fixed, then mass can be calculated from this formula. Similarly, if divergence is fixed at all points, then divergence into volume will give you divergence of field through this sphere. But we use triple integration when divergence is changing, or any physical quantity is changing in a given volume. Then we use triple integration. So this is written in standard form, but you should not think that it can be found only with triple integration. It can be found from single integration also, because many times we find mass of different shapes with single integration. These are just quantities. But standard form it is written in this way. So we will find a problem of divergence with single integration. We will solve it with single integration and triple integration. So we are solving it with single integration only to show that divergence of a field in a volume is not an exclusive property of volume integration, that is triple integration. It can be found by single integration. So it is just a property like other physical property as mass or other scalar functions, temperature, any other scalar function. Similarly, divergence is also proper. So we will take a simple example and solve one by one with single and triple integration. So this is a sphere, and the volume of sphere is given by x square plus y square plus z square less than or equal to 1. Volume of sphere is given by this equation. Similar to line integration, you were having a vector field and a curve. In surface integration, you were having a vector field and equation of surface. Similarly, in volume integration, you will have a scalar field and an equation of volume. You can note down the analogy between line, surface and volume integration. So let there is a function, there is a vector field is given by, in this region, 3xqy. This is x-axis, this is y-axis, and this is z-axis. 3xqi is a vector field. Now you have to find divergence of this vector field in this sphere. So we will find divergence. First of all, we will find divergence of f. It's the vector that is del dot f is equal to, I am directly writing here 9x square. You can find it by del dot f. 9x square is divergence, so it is divergence at different points. So from this equation you can see divergence is it involves x square. So for negative value and positive value of x, this divergence is always positive because it involves x square. So in all coordinates, all quadrants, divergence will be positive. Whatever the value of x is, y and z, it doesn't depend on y and z, but the sphere is in x, y, z space. So it depends only on x coordinate. So whatever the value of x, it is positive or negative, this divergence will always be positive. Now divergence of f, now let us take a small disk. It will be a disk. If we cut a sphere, it will be a disk. Now let us find width of this disk as dx. This is a sphere having radius 1. So this is 1, and at distance x, this is x. So the radius of this disk, this is a disk. Radius of this disk is under root 1 minus x square. By Pythagoras theorem, this is x, this is 1, radius is 1, this distance is x. So radius of disk is this. This is radius of disk, and this is 1 under root 1 minus x square. So volume of this disk is surface area of disk into height of disk. So dV is equal to pi r square 1 minus x square into dx. So now divergence in this volume, we will find by single integration first. Divergence in this volume is x square, that is divergence f, into dV, that is pi 1 minus x square dx. This is integration divergence of f dot e, and value of x will change from 0 to 1. So from minus 1 to plus 1. For whole sphere, it will be from minus 1 to plus 1. Here we are taking whole sphere, unlike in line integration and surface integration, because in line and surface integration, in different quadrants, property, the sign of surface integration and line integration was changing. Hence, we have taken only in a single surface or single curve length where the integration was of similar sign. But here integration is similar. Nature of divergence is positive in all spherical volume. That's what we can take directly. Limit of x minus 1 to plus 1, and this is minus 1 to 1, 9 pi x square minus x power 4 dx. This can be written as 9 pi x cube by 3 minus x to the power 5 by 3 minus 2 plus 1. This can be written as 9 pi 1 by 3 minus 1 by 5 minus minus 1 by 3 minus plus 1 by 5. This is 9 pi 1 by 3 minus 1 by 5 plus 1 by 3 minus 1 by 5 equal to 9 pi 2 by 3 minus 2 by 5 equal to 9 pi 15 10 minus 4. pi 6 by 15, and this is 15 pi by 5. This is 9 pi minus 9 pi 15 10. Here it will be 6 actually. 6, so here it will be 4, and it will be equal to 12 pi by 5. So by single integration we have found that divergence of this vector field in this sphere given equation is 12 pi by 15. So I will write here for comparison purpose 12 pi by 5. 12 pi by 5. Now we will find same thing with triple integration. Triple integration method 12 pi by 5. So here we will find it by triple integration. So for triple integration purpose we have f is equal to 3x cube I. Means divergence of f is 9x square. First step. Second step, you can take small volume having dimension dx, dy and dz in xyz direction. So dv is dx, dy, dz. But you can see here when you will find the limits of x, y, z, then limits will come under root 1 minus x square, under root 1 minus y square, under root 1 minus z square, and the integration process will be very complicated. So we will convert this Cartesian coordinate system into spherical coordinate system, that is polar coordinate system of spherical form. So earlier we have discussed in spherical form dv is equal to dx, dy, dz. And so earlier we have discussed during conversion of Cartesian coordinate system from Cartesian coordinate to spherical form to cylindrical form, that dv is rho square sin psi d rho d theta d psi. Recall this conversion, then you will find x is equal to rho sin psi cos theta, where rho is radius of this circle, psi is angle between z axis and this point P, and theta is angle in xy plane for projection of P dash, and this is x axis, this is x axis. So rho is angle between x axis, sorry, theta is angle between x axis and line OP dash. So in that conversion system, if you will go to that conversion system, you will find x is equal to rho sin phi. This is rho and this is sin phi. So this length is rho sin phi, and along x-axis component is rho sin phi into cos theta, rho sin phi into cos theta. So triple integration you can write as 9x square dx dy dz. When you will convert it in cylindrical polar form, then you can write 9 here. X is this, so you write it rho square sin is sin cos theta square, so you remove it, into dv dx dy is dz, that is this rho square sin psi d rho d theta d psi. Now limits for rho is radius, that is 0 to 1. And so for this whole hemisphere, this theta will change from 0 to 2 pi. And psi, we are taking upper hemisphere only, so psi will change from 0 to pi by 2. This you can write as 9 this is rho square and rho, limit of rho is, so we will integrate with respect to rho first. This is 0 to 2 pi, 0 to pi by 2. So this is sin psi, sin square psi and sin psi, sin cube psi, cos square theta, and this is rho square and this is rho square, so it will be rho power 5 by 5, 0 to 1 d theta d psi. So you can write it 0 to 1, so this is 1 by 5, so this is 9 by 5. Now we know that cos square theta, integration of cos square theta is equal to theta by 2 plus sin 2 theta by 4. Cos square theta, the integration of cos square theta is theta by 2 plus sin 2 theta by 4. This I have already calculated. Cos square theta, you can, this is remaining is 0 to pi by 2, sin cube psi. Cos square theta is theta by 2 plus sin 2 theta by 4, and this is 0 to 2 pi, and now this is d psi. Now this is 9 by 5, 0 to 2 pi by 2, sin cube psi. This is pi. Sin 2 pi is 0. So this will be 2 pi by 2, that is pi, only pi. So pi will come outside. 9 pi by 5, sin cube phi by d psi. So this whole expression will reduce to pi only. Pi. Now integration of sin cube theta d theta is 1 by 3 cos cube theta minus cos theta. This I have already calculated. Integration of sin cube theta d theta is 1 by 3 cos cube theta minus cos theta. You can put it here. 9 pi by 5, 1 by 3 cos cube theta minus cos theta, cos psi, 0 to pi by 2. This can be written as 9 pi by 5 pi by 2. Cos pi by 2 is 0. So this is 0. Minus 1 by 3 minus 1. Cos 0 is 1. Cos 0 is 1 by 3. So this is 9 pi by 5. 1 minus 1 by 3. And this is 9 pi by 5 into 2 by 3. And this is 6 pi by 5. So we have calculated it for upper half hemisphere, 6 pi by 5. For total sphere, it will be 2 into 6 pi by 5, 12 pi by 5. So you can see 12 pi by 5, 12 pi by 5 it was calculated from single integration. So with the triple integration and single integration, result are same. So that was just, I have tried to explain that divergence is not a property of volume integration, triple integration. So that's why I have calculated from single integration also divergence in this volume for a field. Similarly, in short, we can say that by single integration, we have successfully found line integration, surface integration, and volume integration. By single integration only, we have found line integration, surface integration, flow problem, and volume integration, that is divergence problem. Similarly, surface integration we also found from double integration also, which was similar to single integration. And similarly, we have found here divergence in this volume by triple integration, which is also equal to divergence found with single integration. That is, this was found with single integration and this was found with triple integration. So, but in vector calculus, you will find that these things are written in standard form. So you should not confuse that. So I will write how these are written. Line integration is written as C A to B F dot dl. You will find line integration like this, and that you can easily, we have explained the big problem. And surface integration is written as this, region R, for a region R, F dot dA. This surface integration, we have also found the problem of flow with the help of single integration. This is just the representation purpose, surface integration. And this can also be represented sometime with single, a surface F dot dA. And volume integration in terms of divergence is written like this, divergence dV and volume. This is also written volume divergence. So most frequently it is written in this form, and surface integration is written in this form. But you can write divergence with single integration terminology and surface integration with single integration terminology also, and you can find them with single integration also. So that we have tried to explain here, to not think that the surface and divergence are exclusive property of double and triple integration. They have nothing to do with type of integration. They are just property, and you can find them with the help of any mathematical method. If they are not changing, they are not varying, you can just find by multiplication of arithmetic multiplication. Single multiplication you can find line integration, surface integration, volume integration by single multiplication. But if the quantities are changing, then you have to apply integration. And don't think only surface integration can be found with double integration or volume integration can be found with triple integration. Only single integration can also be used as a mathematical tool to find surface and divergence problem for a given area and for a given volume. So that was the basic terminology of vector calculus, that is gradient, field, and this curl, divergence, line integration, surface integration,